teaching point, I'll be able to use the rock cycle diagram to understand the three types of environments rocks can form in. Launch. Why does it take so long for rocks to go through a cycle? All right, let's think about this. All right, surface rocks breakdown. We just had a unit on breakdown for weathering due to weathering and erosion. Five agents of erosion: glaciers, running water, ocean waves, wind, mass movements, getting transported and deposited underwater. Uh, Most dense, largest, roundest settle first. Least dense, flattest, smallest settle last. Layer upon layer upon layer upon layer all comes in there, goes through compaction and cementation to produce a sedimentary rock. And then this can get buried deeper underground, increasing heat and pressure. This rock can turn into a metamorphic rock, right? Or this sedimentary rock can slowly be forced back to the surface, like uplifting forces. If it turns into metamorphic, this can slowly be forced to the surface. Right, this metamorphic rock can also melt. It can melt, turn into molten rock magma. It can crystallize, producing igneous rock, which makes up the land. Right, or it can burst through the surface, creating an explosion. Lava at the surface, volcanic eruption. All right, so why is this process so long? It doesn't take a day to weather. It takes thousands of years, maybe hundreds of thousands of years, hundreds of millions of years. Right, this sedimentary rock process is a long time, right? That's the part of the biggest process that we have. All right, so if you're looking at page 6 of the reference table, you see that green, right, is a very long process going across. This is your clastic rocks. Uplift, weathering, and erosion, making sediments. That's the key thing, sediments. So this is really good for your clastic sedimentary rocks because they'll have grain sizes. Oops, sorry. Zoom back in. That's what I need. Okay. Conglomerates have an assortment of sizes from boulders down to clays, as well as breccias. Sandstones have sand grains, fine to coarse. That's what it says here. Siltstone, right? You have a arrangement or a range of sizes for silt. And then you have shale, which is going to be your clays. Right, and those are all these types of rocks that can form. Once you form sediments, you have to get deposited. And then it's going to take a while for those to get buried. They have to get buried to get compacted. And then any leftover water in between the grains will get so saturated with salt water that the solids come out of solution and begin gluing these sediments together, cementing these sediments together, giving you sedimentary rock. These sedimentary rocks can also go right back into the process of uplift, weathering, and erosion into sediment so it can become itself again over and over. The blue is igneous rocks. We have melting, so sedimentary rocks can melt, metamorphic rocks can melt, igneous rocks can melt again, giving you magma, which is molten rock below the Earth's surface. And eventually that needs to solidify to become an igneous rock. If we have heat and pressure, igneous rocks under heat and pressure can turn into metamorphic. Sedimentary rocks under heat and pressure can turn into metamorphic. And in addition, metamorphic can go right back into itself again with more heat and pressure. But it takes a long time for this to occur.
The Science Guy, brought to you by rocks.
Did you ever stop to think that the whole world is covered with rocks? And every rock used to be different. When you're looking at a rock, you're looking at history.
Careful.
See, all the rocks in the world used to be melted rocks, what we call molten rocks. Molten. Like this molten rock in here. And you see the bubble on top? It's from the heat. It's just like the rocks that come out of volcanoes. Rocks like this, rocks like this, rocks like these. See these pits? They were formed by bubbles and liquid rock that came out of a volcano. Now sometimes the rock from volcanoes will come up onto the Earth's surface. Now when these rocks get on the Earth's surface, they push other rocks down. It pushes down on the layers below. Push the old rocks down. Push them down, and they'll squeeze together and swirl around. And when they blend together, they form a new type of rock, like the minerals that are swirled together in this piece of marble. Anyway, wind and rain moving over the Earth's surface break rock down into sand. Sometimes enough water will flow through the dust and sand, mix them together, push it around, it'll dry out again and turn back into rock like these. Good thing I have my safety glasses on. Now this process where rocks are formed, broken down, and reforming as they come out of the molten earth and turn back into dust, into rocks again, has been going on since the world was formed. Billions of years ago. Rocks! Rocks!
Rocks are formed in different ways. All the material in this sandstone once belonged to other rocks. That rocks.
Scientists like to think of 3 types of rock. Now, the first type you might call igneous rock. Igneous rock. Now, igneous comes from the word for fire. You know how you ignite the candle and you have igneous rocks? You know, igneous, ignite, that's from the word for fire. So see how the candle wax drips down the outside of the candle? Well, igneous rocks are often formed when hot lava drips down the outsides of volcanoes, and it cools to form rocks like this granite. The next type of rock we call sedimentary rock. Now, sediment, that's silt, mud, goop in rivers. So if you have a river and it's washing sand, mud, or silt, sediment, downstream, well, eventually the river may dry up or drain away, leaving the sediment, the sand, silt, or mud. Now, this sand would be heavy. It crushes down on itself, like this, squeezing itself together. Till eventually, after the water is completely drained away, after a few thousand years, you end up with a rock like this one. See the layers? Sedimentary rock often has layers in it because that's the way sand washes downstream in a river. Now, the last type of rock is sort of a combination of the other two. We call it metamorphic rock. Now, metamorphic means it's changed, it's metamorphosized. So, if you look at this is rock that was once sand, but it's been smushed together by huge pressures under very high heat. Pressure and heat, smashing the rock till it's just crushed flat like this. See, heat and pressure formed another rock.
The Science Guy, brought to you by rocks.
Did you ever?
All right, so rock, a naturally formed solid composed of one or more minerals. All right, so as you get this down, great question is how did this rock get there. Right now we see layers. We just heard that layers, that's how sand grains would form, right, into these layers. We can see it light color here, dark, light, dark. Same type of layering that you see if you've been to the Grand Canyon before, layer upon layer. All right, this is 2 scale, where we can see these individuals here. This is a massive boulder sitting on top of this rock. So, few ways that this can form, right? One way here, I see a cliff, right? And one thing that you can think of is maybe this was a rock fall. Right? Maybe this fell off the cliff and just landed here at the base. That can be that's one way. Second way, of course, can be a glacier, right? Maybe this, depending on what state this is found in, more than likely this might be a very warm climate area. Highly unlikely this would be a glacier, but could have been a glacial erratic. All right, and the last one could have been wind. Now the wind cannot carry this tremendous boulder. This probably could have been a mushroom-shaped rock, and then it got so eroded at the base that the top part of this mushroom shape just fell down onto itself. All right, let's continue. Rocks can be monomineralic or polymineralic, right? So the prefix mono means one, right? Contains only one mineral. Poly means more than one, right? Contains 2 or more minerals in these rock samples. The majority of rocks are polymineralic. You will have some rocks that are strictly containing one mineral only. All right, like for instance, limestone. Limestone contains only calcite in it, and therefore limestone is a monomineralic rock. All right, continuing, rock cycle, a diagram showing how closely the rock types are related. They are related because they can all turn into themselves. Sedimentary can turn back into its own self again, as well as going into igneous or metamorphic. Metamorphic can go into igneous and sedimentary, as well as go back into itself. Igneous can become sedimentary, igneous can become metamorphic, and igneous can also turn back into itself. All right, so a diagram here showing how closely the rock types are related. All right, a few definitions. We have igneous, formed from the cooling and solidification of magma or lava. Oh, thank you. Sure. Okay. All right, formed from the cooling, key thing, cooling must cool down, and it must solidify to make igneous rocks. If they don't cool and solidify, they're going to be in this molten state. Molten means liquid rock. All right, this picture that you see here is what type of rock? Is it molten rock lava or molten rock magma? If I gave you that hint, you probably can get the answer. Right? But if I ask you what type of molten rock that is, a lot of you would just say, oh, that's magma. It was once magma, because this was once below the Earth's surface. And once this exploded and began flowing on the surface of the Earth, we call this molten rock lava. We have some funny names for this. The funny names is in reference to Hawaiian names. One type of flow is called pahoehoe. Pahoehoe is kind of like a runny nose lava flow. It flows really quick. Less viscous. You have ones that have high viscosity, right? They kind of move slow. You can definitely outrun those flows. And they're called aa. Just the letter A, letter A. So you got pahoehoe flows and aa flows. All right, igneous rock in this sequence here, sedimentary rocks can melt, metamorphic rocks can melt, igneous rocks can also remelt again to form molten rock magma below the surface, and that must cool and solidify to make igneous rock. Now, I don't like this diagram too much here because if we see magma, we're kind of only inferring that this box here is intrusive igneous rocks, right? Because in reality, intrusive and extrusive, you colored this in yellow and red. Your reds were intrusive rocks, your yellows were extrusive rocks. But magma deals with intrusive rocks. Right here, rock cooled down from volcanoes. We can see those holes and pits. I like to call these fossilized gas canals. So what happens here is as this molten rock was cooling, it had gases trapped inside of it. Now, what's more dense, liquids or gases? And the answer there is, right, the less dense is going to be your gases. So the gases escape this mass, and as it does, it can leave behind the pathways that the gases escaped. That's why I like to call these fossilized gas canals. All right, here's magma injected into other rocks. So we have like these diagonal stripes going across. Here's one, and here is two. So here is some pre-existing rocks here. This gray or blackish color rock, and this magma source, this molten rock, which is light in color, went through this pre-existing rock. So more than likely, this is definitely going to be some sort of intrusive origin here. And on this sample, this is definitely above the Earth's surface. This has to be lava, and this has to be extrusive igneous rocks. All right, moving on. Sedimentary, formed from the compaction and cementation of sediments or from precipitates in a evaporating solution. So whenever you have a solution, for instance, if you go to the beach this summer and bring home a container of ocean water and you leave it outside or you leave it in your house for a few days and just let the water evaporate, what's going to get left behind is all the salts that were in that salt water. So the salts are dissolved in the water, and when the water evaporates, only fresh water is evaporating. Only fresh water is. All right, and since fresh water is evaporating, we're going to have that fresh water in the atmosphere producing clouds. And that rain that falls is pure water, right? And that's salty water. All right, so we got some layers going on here that we can see. Going across. We definitely have some talus at the base. We have some, most likely this is a cliff. So rock falls, talus, physical weathering here at the base. Again, this is really only clastic sedimentary rocks, nothing to do with precipitates. All right, your precipitates are here. So under the crystalline rocks, and limestone can also be crystalline, so we have 4 rocks: rock salt, rock gypsum, dolostone, limestone. These 4 rocks are formed from crystals from chemical precipitates and evaporites. So when the fresh water evaporates out of this saturated solution of salts, your salts precipitate out of solution and would fall at the base of your container or the base of the basin. All right, here are some more examples. Here is the Great Salt Lake. in Utah. So it take whatever was dissolved in that water. Here is your basin. This water evaporates, and what gets left behind is going to be your salts, whatever was in solution. Right, here's kind of a close-up picture of it, and you can see the salt crystals forming, right, as the water evaporates. It's pretty cool. Sedimentary rocks, we have some layers going on. This is sandstone, of course. Sandstone can be in a nice layer-like area. You have different orientations of it, so sometimes some of these rocks can be preserved like in dune shapes. Sometimes they can be in different environments. They can be underwater over time. So you have different climates that can happen because of the plates moving. All right, next one, metamorphic. Formed from intense heat and pressure, forcing rocks to recrystallize its minerals. So this heat and pressure builds up and does not melt the rock. It's just going to recrystallize. It's going to become heated enough so that the rock becomes maybe more of a soft solid, not in liquid form though. And it's pressurized, and you can begin seeing some of these distorted layers. So they're not perfectly straight, right? This picture was taken. These look like horizontal lines going up and down. They can be vertical. They can be horizontal too, but these lines are distorted. They're not perfectly straight anymore because of different pressures inside the earth. All right, so here we got the heat and/or pressure. That's the same thing happening here. So all three rocks can be metamorphic. The key thing is that it cannot melt. If it melts, that's dealing with molten rock magma and becoming igneous if they melt. All right, here is some intense warping of rock. So we see these layers, right? Almost like peaks and valleys going across. If this was a graph, you know, like a graph line, here's your y-axis, here's your x-axis, almost like a cyclic or cyclic looking graph. But this is some intense warping of rock. This is banding. Special type of rock. All right, so here is the cycling of rocks once again. So we have a lot of forces on the surface that can help break down rocks. Weathering of rocks at the surface, exposure near the surface. They'll become eroded and transported to your basins. In your basins, such as the oceans or lakes or ponds, you would have deposition of sediment. And you have deposition upon deposition upon deposition, layer upon layer, which helps bury and compact the sediments. And this will help lead that into becoming sedimentary rock. As this rock maybe gets deeper inside the earth, heat and pressure builds up. Deformation, metamorphism turns that into metamorphic rock. And if the heat builds up too much, that rock mass can melt. Right? This is molten rock magma below the surface. And what's more dense? Solids or liquids? Most earth materials, more dense would be your solids. So this is in liquid form. The liquid's going to be less dense. It's going to rise toward the surface and making some of these mountains volcanically active. We do have the word uplifting forces here. So sometimes when you have tectonic plates, Like in this picture, we have a plate moving down and a plate moving across. This can force some of the plates to move up vertically, giving you higher mountains, like the Himalayas. All right, there is a time to climb. All right, I will post that up for you so you can work on some of these questions during class time. All right, I'll put the student paste so you can work on that. All right, that concludes this lesson. Okay, that's it. That's fine.